So hello and good afternoon. Welcome to today's session on the Umetrics suite of data analytics solutions. Today's presentation has the title Part 7 OPLS in Process Modeling. For those of you that have not attended this series of webinars in the past, we have here a little overview of the different components or elements making up the Umetrics suite of data analytics solutions. And in the beginning of this webinar series, we started out by looking at the model software for design of experiments and quality by design to get things right from the start. We have also penetrated the easy analytics solution to help you make everyday data decisions efficient. And right now we are in a series of webinars going through the data analytical capabilities of the SIMCA software for multivariate data analysis. And gradually towards the end of this series of webinars, we're approaching our online solutions where we have SIMCA Online, the Control Advisor, and finally the active dashboard. But today we are going to talk about the OPLS tool and how it applies in process modeling. Now, as a general introduction to this topic of today, we can say that there are a couple of data analytical engines that are often used when you are modeling process data, and the mother method is the principal component analysis method. PSA applies when you have one type of data, which we can call the process input data. Usually in statistics, that data table has the capital X as a notation. And when you have one block of data, what you're doing is that you're trying to build a model on good data, data representing good process behavior. And in a validation step, you try to verify that this model can distinguish between good and bad and also be used for online monitoring in the long run, trying to extract early warning of disturbances. And if you're finding disturbances, it is also important, of course, to be able to understand why a certain event has occurred. So in other words, you're trying to interpret the deviation, finding the assignable causes. On a slightly higher level of ambition, you still sometimes also have access to a second block of data containing one or more process qualities or process outputs. And then you are using regression extensions of the PSA method that are called PLS and OPLS, which are primarily the OPLS is in focus here. And using these tools, you try to interrogate the process inputs, looking for information that can be used to model and predict future process outputs. The regression problem also occurs for batch processes, and with batch processes we have even more complicated arrangements of data. We still have this block of process inputs that are measured or apply at the start of the different batches, but in addition we also have measurements reflecting the evolution of each batch, and this can be process measurements, but it can also be spectroscopic measurements and in-process IPC data measured at the discrete time points during the progression of the batch. And then you are linking these, what we call initial conditions and batch evolution measurements or process inputs to different process outputs in the same way. So we are going to take a deeper look into the regression problem using PLS and OPLS, and here we have an overview of the let's say different sorts of data tables that are normally occurring in a regression problem. So for a training set of observations, you are measuring what we call process inputs, process parameters. For the same set of observations, you're also measuring one or more process outputs, qualities, yields, throughputs, and so on and so forth. And then you are trying to use PLS and OPLS to find relationships between these data tables, find information overlap between the process input data and the process output data. And if you can establish such a model, the idea is then in the long run to measure equivalent process inputs for new observations, making up the so-called test set or prediction set, insert that additional process input measurement information into the model, and at the other end, so to say, get out predicted output values for the new observations. PLS and OPLS, they are then useful to investigate the information overlap between two blocks of data that are often called X and Y. And it's fair to say that these methods are regression extensions of the mother method, PCA. PLS, first of all, is short for partial least squares, and it was originated around 1975 by Herman Wold, who is or was a professor of econometrics at Uppsala University in Sweden. In the early 80s, it was refined and improved to become what it is today by, amongst others, his son, Professor Svante Wold. And about 20 years later, there was another improvement which was given the name Orthogonal-PLS, which was introduced around 2001-2002, and that was developed by Professor Johan Trygg. And OPLS is interesting because it offers an enhanced or simplified model interpretation. But if you're comparing or co-charting, benchmarking a PLS model and an OPLS model for the same data set, and you're comparing models with the same number of total components, they are absolutely identical with regards to prediction if you're modeling just one Y variable in the model. So there can never ever be a claim that one model outperforms or one tool outperforms the other with regard to prediction in the single Y case. On this slide, I will try to explain a little bit what is the conceptual difference between PLS and OPLS. We say that these methods are projection-based. It means that we are in input space and output space trying to look for simplifications, trying to find directions among the points in the X space that overlap with the configuration of points in the Y space. And here the information overlap is represented by the colored structure. So what we are trying to do is that we are projecting a complicated reality down to a much lower dimensioned subspace, here exemplified by one latent variable, one new index in the input space, and another new projection index in the output space. So in the simplest case, PLS will find these colored structures and find out what the information overlap is, or we can also say PLS tries to find information in the X block that is of relevance for modeling and predicting the Y space. And as long as the colored structure dominate, PLS will work very well. Now sometimes in different data sets and different applications, there can be other sources of systematic variations between the samples. And we here designate that sort of additional systematic variation by the gray dots. Such information that is systematic can exist both among the process inputs and among the process outputs. But when the gray structure, which is present in only one of the two blocks, is larger than the colored structure, then PLS runs into trouble. And it is here we then have an interesting application of the OPLS tool, because OPLS is able to filter off or filter away the non-correlating information that we here symbolize by the gray dots and still find the colored structure. We see on this slide another typical way of comparing PLS and OPLS. We have a normal single Y multivariate calibration application, and to the left we are plotting the score plot for the PLS model for the first two components. The horizontal dimension is represented by the first component and the vertical dimension by the second component, and each dot is one sample, and then we're coloring all samples according to changing levels of the analyte concentration or analyte level of the analyte in question. So we can see that in the case of the PLS model, both components are needed to fully account for the changing analyte levels. Whereas on the right-hand side, we see that with the OPLS model or the OPLS technology, only the first dimension of the model is needed, because we can see that when we're going from left to right along the horizontal dimension, we have increasing level analyte concentrations of the analyte of interest. So one way to see OPLS is that it is a rotation or a transformation of the PLS solution. And as I said on one of the opening remarks, we always emphasize that OPLS and PLS models on the single Y scenario where the models have the same total number of components are completely equivalent from the predictive power point of view. Sometimes we use this slide also to further enhance the difference or contrast between PLS and OPLS. In this slide on the left-hand side, we have the amount of variation explained by the model for the PLS model on the left-hand side. And what PLS is capable of doing is to divide the variance of the X block of the process inputs in two parts. The explained variance, which we normally call R square X, and the unexplained X variance, the residual, which we normally represent by the capital letter E in the matrix notations. And it is from this non-explained variance, the residual parameter D mod X is computed for each observation. OPLS has an ability to further split this systematic variability R square X in two parts. The part that is correlated or predictive to the Y, R square X pred, and the part that is not correlated, that is orthogonal to the Y. Sometimes this blue field here, the R square X orth, is 0, and then OPLS goes back and becomes equivalent to the PLS model. This ability of OPLS to divide the variance of the X block in three parts also has consequences for the model structure. So on this slide we see the OPLS model for the single Y situation. For the single Y situation, there can always only, by theory, by definition, be one single predictive component, but it will have a score vector and a loading vector on the X side, a score vector on the Y side, and then the single loading element Q. But there will be 0, 1 to 2 too many so-called orthogonal components, here represented by the red color, capturing or accounting for the systematic variability in the X block, in the process input block, that is systematic between the samples but not related to the Y variable in question. We will now move into our first example. The first example is actually a two-stage data set where and it is a feasibility where we call it binary powder 1, if you are familiar with our tutorial examples. All the work comes out of AstraZeneca in Södertälje, and the main driving force behind all these investigations is Dr. Ola Berndtsson. And in this feasibility study, they were studying, Ola Berndtsson and co-workers were studying the mixing of two powders, binary powders, where the powders had similar particle sizes, and this represents a common situation in pharmaceutical production. The two model powders are lactose and salicylic acid, and when preparing the training data, so to say, mixtures of these two powders were prepared ranging from 45% up to 55% salicylic acid. So what we're going to study now is the applicability of OPLS using this sort of scenario. We are having an X block of data, process inputs you can say, which will be spectral measurements, and we're having a single Y variable, which will be the content or the amount or proportion of salicylic acid in the different batches of powders. So the total data set contains 12 batches of powders where the salicylic acid content ranges from 45 to 55%. 6 batches were positioned in the training set, and the other 6 batches were positioned in the test set. And for each batch, 40 NIR spectra were acquired, and they were then acquired by modifying the positioning of the fiber optic probe against the powder surface in 40 randomly chosen positions. So the total numbers of spectra were 480, 12 times 40, and 240 of these spectra went to the training set, and the other 240 went into the test set. The NIR spectra were measured in the interval 1000 to 2500 nanometer, and with the resolution that was used, this corresponds to close to 1600 X variables. So on the right-hand side, we have an overview of the matrix structures that we have. We have the training set, and what we will try to use PLS and OPLS to do is to see if there is any information in the NIR spectra that is correlated to changing levels of the percent salicylic acid among the training set samples. Later on, we will also insert the data of the test set and make predictions for the test set and compare predictions with real measurements. Before we start to develop the model, it's always good to inspect the incoming data, and in the top part here of the slide we see the spectra of the training set samples. So we have a total of 240 spectra here. There are some level shifts or baseline differences. This could be in part due to different percentages of salicylic acid, but it could also be other systematic changes, so we should bear that in mind. For comparative purposes, we have also visualized on this slide the spectra of the pure components, so to say, salicylic acid and lactose, and I will come back to those in the interpretation in a few slides to come. So what we will do now is that we will use PLS and OPLS and develop two models side by side and compare them based on the training set and see if there are information in the NIR data that can model and predict the salicylic acid proportion. The PLS and OPLS models both have 7 components, and they have, as expected, identical performance. Of the 7 components, we are modeling close to 99% of the spectral variance, and the R square Y of the Y variable is 97%. The additional information that is coming out of the OPLS model is that out of these 99% of the explained X variance, only 22% is correlated or of relevance to the Y variable. So only 22% of the variability in the NIR data is connected to the variation in the levels of the salicylic acid. The remaining 77% in the NIR variance is systematic but not connected to the Y variable. That is the little piece of extra information coming out of the OPLS model. We are now looking at the first 2 score vectors of the PLS model and the OPLS model. We have the PLS model to the left and the OPLS model to the right, and all samples are colored, I should say, according to the percentage of salicylic acid. So we have a gradient here from 45 to 55% salicylic acid, and you can see that with the PLS model we need 2 components to account for the Y, whereas after using OPLS and the rotation that OPLS will inflict or accomplish on the data, we need only the first component to fully account for the changes between the batches. So this leads to a more crisp understanding what the different components mean. The horizontal change from left to right in the OPLS model represent between powder batch variations, and the change from bottom to top in the vertical dimension represents within batch variations, and we can then follow up with the loading plots trying to figure out what the between batch variation and within batch variation look like from the spectral signature point of view. We do that on the next slide. On the top part we are plotting the predictive loading, the black line, and we're plotting the first orthogonal loading, the blue line. And one interesting thing is that the first orthogonal component of the OPLS model, the loading of that component is constantly on the same side of the 0 line, suggesting some sort of baseline structure associated or changing levels, at least between the spectra, associated with this orthogonal component. And this systematic change is not connected to the changing proportions of the analyte in the samples. In the lower part of the slide, we are plotting again the black and the blue line, but we have added a third curve, and that is the red line, which is the difference spectrum. It is the difference spectrum between salicylic acid and lactose. If we compute the difference spectrum between these two pure spectra, it will be like the red spectrum on the current slide. And we can see that the difference spectrum is very well aligned with the predictive component of the OPLS model, and that will then help us in the interpretation. When we created this plot, we also rescaled all the numbers to run just between a 0 and +1 representation in order for them to be easy to plot in the same plot. Additionally, we may proceed. I can go back again a couple of slides. We now have looked at the model and its performance statistics. So we now insert the NIR data of the test set into the model and make a prediction of the amount of salicylic acid for the different samples in the test set. Conventionally, you are often co-displaying the relationship between estimated and measured data for the training set, and in a separate plot, the same estimates from the model and measurements for the prediction set in a separate plot. So in the left-hand part, we have the relationship between measured salicylic acid on the y-axis versus the estimates coming out of the model for the training set, and in the right-hand plot we have the similar scenario but for the tested samples. So in both cases there are good agreements between estimates and predictions. We have a couple of statistics in the footer of the different plots summarizing the fit and the predictivity, and these are the so-called root mean square error of estimation statistics, root mean square error cross-validation statistic, and the root mean square error of prediction statistic, and they are also summarized up here. And what is particularly encouraging is the similarity of the cross-validation counterpart and the external prediction statistic. They are very similar, suggesting a very good and well-founded model. So the conclusion from this first stage were very promising and encouraging, and the researchers then decided to take on the second stage of this feasibility study, where they, so to say, got a little bit braver and spanned the space more. So instead of looking at binary powder blends where the powders had similar particle sizes, they were now looking at mixing of two powders with very different or marked differences in particle sizes. One powder with a fine particle size and one powder with a much more coarse powder size. And also, instead of going between 45 to 55%, they span from all the way from only a fine powder up to just 100% coarse powder. And these changes were then made in steps of 10%, so 10, 20, 30% coarse powder. So this gave a total of 11 batches. The training set was made up of 6 of the batches, and now instead of measuring only 40, they measured 100 spectra. So we have 600 spectra in the training set. Similarly, we have 500 spectra in the test set. And based on some of the findings of the initial study, they were also modifying both the spectral window and the resolution. So this was the spectral range, and with the resolution used, there was, so to say, a little downsizing as far as the number of spectral variables was concerned, down to 280 variables. And part of this was also because they were measuring something called a monitoring set with 6,000 spectra. So the scenario here is that we will first try to establish a model using the same workflow as we did for the binary powder 1 dataset. If that is successful, we will then apply that model on a more real-world data set, you can say, the monitoring set. And the scenario is as follows, that in the monitoring experiment, they have access to a mixer. The mixing equipment is like a conical mixing equipment. And first, only fine powder is loaded into the mixer, so the fine powder will be in the bottom, and on top of the fine powder, equal amounts of coarse powder is loaded on top of the fine powder. So you will have 50% of both types. Then, when the experiment is starting, there is an orbiting screw which is rotating. and that orbiting rotating screw will then create a convective mixing mechanism, and the progression of the mixing experiment is then followed by inserting a fiber optic probe through a hole in the cone wall, and the question is, when is the mixing complete? They are measuring around 6,000 spectra. That corresponds to somewhere around 20-21 minutes of operation of this mixing experiment. So making a long story very short, the first stage was very successful. A strong model was obtained. When inserting the test set data into that model and making predictions for the test set, very, very good results was acquired or accomplished, and that inspired the researchers to apply that model to the monitoring set, where there of course is no answer, and the question is, when do you have a stable prediction of the percent coarse powder? And we can then, as you see in the next slide, use control charts to try to visualize that. So in the top control chart we have from 0 to 6,000 spectra. That is the time order, approximately a little bit more than 20 minutes of operation. And on the Y scale we have the percent coarse powder predicted by the model by measuring the NIR measurement then. We can see that in the beginning the fiber optic probe is not seeing anything but the fine powder. So at the onset of the experiment only fine powder is found in front of the probe window, and then in the beginning there are rather large fluctuations, cyclical fluctuations, but after a while the amount of coarse powder, the predicted amount of coarse powder, stabilizes around the expected 50%, and you can see that that stabilization occurs after around 2,000 spectra, which means about 1/3 into the sampling campaign period. So the conclusion from this experiment would be that about 1/3 into the sampling period, the mixing is fairly stable. Now, for a data analytics nerd, perhaps just a few side notes. You can see the spikes here. There is a spike for every 140th spectrum, and that is when the orbiting screw is passing in front of the probe window, so to say compromising that particular spectrum. Now, there are tools to address this, and in the lower part we present another type of control chart where we are working with the subgroup formation and counting or calculating the average inside each subgroup and the standard deviation. And by doing that little manipulation, we can see that we have a smoothing effect of the average group of the average in each subgroup, and that the spikes are flushed out to the standard deviation control chart. Here we are using a subgroup size of 14, which means that it says here sample size 14, which means that the spikes here come at every 10th subgroup. But that was a little side note. The main conclusion here was that PLS and primarily OPLS was very successful, and the results of this study was really encouraging and indicated that NIR was suitable for monitoring this mixing experiment, and that OPLS modeling of the relationships between the NIR spectra and the various Y variables was a very good and fruitful approach. We are now moving over to the second example where we are looking into a batch reaction. So we are going to review some results that we published 2 years ago in an article in Analytica Chimica Acta, and where we are basically looking into the applicability of PLS and OPLS for batch monitoring. So we are now going to look into an application of the bottom type, where we have, you can say, a more complicated arrangement of the data, more advanced architecture of the data. First of all, we're going to look into how PLS and OPLS operate in the different modeling stages of batch data. In the SIMCA software, we're talking about 2 types of models. We have the batch evolution model and the batch level model. And these 2 types of batch models complement each other, and they are accomplished using different types of unfoldings of the data or arrangements of the data. So first of all, we have data for a certain batch. We have a batch start and make a lot of measurements over time until batch finish, batch end. Then the second batch starts, we make similar measurements until batch termination. Third batch, measurements in the beginning till batch finish, and so on. What we can do is that we can also modify, we can slice and reorganize the data, what we call batch-wise unfolding. So each variable is transposed and aligned to make one row per batch. So each completed batch will be one row in the alternative way of arranging the data. And when we are using this last sort of configuration of the data table, we're making the batch level model where we are comparing completed batches. When we are working with the more left-hand arrangement here, we're looking at the individual time points of the different batches, and that is more where we are focusing on the evolution of the batches. In this data set that we are soon going to look into, we are making a batch evolution model, and in the batch evolution model, we need something to give the model a direction. So in addition to this sort of arrangement where we have the process inputs, we also have a process output or a Y variable that can be a time or a maturity indicator. It can for instance be the amount of ethanol in beer brewing. A maturity indicator is something that reflects the progression of the batch. Either the time or a maturity variable is used in conjunction with all the other process measurements in order to give the model a direction. This is now called the batch evolution model, and from the batch evolution model we can create control charts. Some more details about the application. It is a hydrogenation reaction where we are looking into a conversion. There are 6 center point batches, normal operating condition batches, reflecting how this reaction normally proceeds, and they are used for model training. In addition, there are 5 batches that we can use for model testing. 3 of them will come from the corners of a DOE that I will present on the next slide. And there are also 2 additional batches where more elaborate and deliberate process changes, process upsets were induced. To reflect the progression of the batches, there were a number of process variables measured, 87 variables. It says 88 here, that is a typo. We had 80 spectral variables. Also being pre-processed using the first derivative, and 7 more, let's say, conventional process variables. These conventional process variables were reactor temperature, reactor pressure, gas feed, jacket in and jacket out temperatures, flow rate of oil, and stir speed. And here is the reference for the original data source for this application. So the hydrogenation reaction concerns a reaction where we are converting nitrobenzene to aniline, and there were 2 regulatory parameters that were modified in the DOE. It was the temperature and it was the initial concentration of one of the reactants. One of the corners of the DOEs failed miserably, and there were 6 center points done in order to encode the normal operating condition. And then there were these 2 process disturbance batches where more deliberate changes were induced. So we will now use these 6 normal operating condition batches and develop a batch evolution model. So the 6 center point batches encoding normal operating conditions were unfolded like this, and then OPLS and PLS were used to make the models. These models are shown here. We have a model with 3 components, and we can see that 84% of the variability in the process measurements and the spectral data can explain close to 96% of the time variable. The OPLS model tells us that out of these 84%, only 65% is predictive to the Y. The remaining 19% in the spectral and process measurements, that is systematic, is not correlated to batch progression. What we're then doing is that we are developing control charts, and with the control charts we can then visualize normal operating conditions. We see here two control charts, and they are understood as follows. We have batch start and batch end. We have lower and upper control limits corresponding to plus and minus 3 standard deviations, and the green dashed line, that is the golden trajectory. That is the average trajectory across the 6 normal batches. And we also see that one of the batches can be displayed like this. When we now apply these control charts to one of the test set batches, in this case the top right-hand corner, where we have the high setting for both DOE factors, high temp and high initial concentration, we see both in the PLS model and the OPLS model that this has to be a rather fast batch producing a high amount of product. PLS will initially find the progression of this batch to be in line with the normal operating condition up to about 10 minutes, whereas OPLS will directly flag that this is a very different batch compared with the normal operating conditions. So PLS is not as sharp and capable, you can say. Another case comes from this DOE combination, where we have low setting for the temperature and high setting for the initial concentration. This is a batch that is slower and produces lower amounts of product. OPLS consistently shows this in the score plot, whereas PLS would claim that for a rather long part of the duration of this batch, it progresses according to the development trajectory of a good batch. And the reason why you have these differences is that PLS is mixing up predictive and orthogonal variabilities, whereas OPLS is able to separate this out. Regardless of whether we are making you can say models for processes of the continuous type, like with the binary powder example, or of the batch type, like the last example, the ultimate goal should be to deploy created and validated models in an online deployment. And we then have, of course, the SIMCA online software that we're going to discuss in more detail in a couple of webinars towards the end of this discovery series of webinars. So I'm just highlighting the possibility to deploy models of this type in an online scenario. This brings us to the software demo, and we're now going over to the SIMCA software, and the data set I will demonstrate is the first stage of the binary powder mixing experiment. We will import the data. We are locating the data for the binary powder 1, the training set, and then we will be asked a couple of questions. So whenever you're importing data from an Excel file, you can import data from a workbook with multiple sheets, and there are different options then. You can import data in terms of separate sheets, but you can also merge them in different alignments. In this case, we're going to import the NIR data and the Y variable as separate sheets. So we will get one tab for the training set, the spectral data, and another tab for the Y data. I will not go through all the details here because how SIMCA is operating we have also discussed in earlier presentations in this series. But briefly, SIMCA will need at least one primary identifier for each row and one primary identifier for each column. And you can think of an identifier as a name or a label. And you can then also optionally have secondary identifiers. So everything is according to expectation for the NIR data. But regarding the Y data, we will have to assign that this column is a Y variable. If we are not saying anything, SIMCA is silently assuming that all columns that are imported will be an X variable, but the Y data here should be a Y variable. We will now finish and be guided over to main SIMCA. I did the rehearsal earlier, so I'm overwriting these results. We will now have two data tables. we have the process data, the spectral data, and the Y data. And for instance, if we would like to verify that the import seems to have gone according to expectation, we can always make a little plot of the spectral data using the Spectra button here. So here we see the 240 spectra making up the training set, and we will also now in the demo here look into what options are available to try to align the spectra better, try to compensate for the shifts in the baseline levels. But before we do that, what we will do is that we will calculate a PLS and an OPLS model. In order to do that, we have to define a work set, and we will have to kick alive or take into account also the Y data. Those of you that have attended earlier presentations know that the workset dialog consists of a series of tabs where you can do different changes and settings and pre-processings. And what we will do here is that we will go to the scale tab, because we will prefer to work with the NIR data only being centered and no scaling. We don't want the unit variance scaling, and in previous webinars we have discussed different options for scaling and centering. If you go back to webinar 5, I think it was. So we're going to say OK, and we will calculate an OPLS model. It has 7 components. We will also calculate the alternative PLS model, which hopefully also will have 7 components, and yes, it has. So we can minimize these 2 plots. And just for comparative purposes, I am opening up the windows for the different models describing the summary statistics, just to verify that you can see that both models have 7 components, although in the OPLS model we would be talking about a 1 + 6 component model. What is of interest is to plot the score plot of first the OPLS model, and we can remove the numbering, and we may also color according to identifiers. I'm using part of the name, so now we have color coded the score plot according to a percentage of salicylic acid. We can make a similar plot of the OPLS model and arrange them side by side. So in the left-hand part, we have the results for the PLS model, and in the right-hand part, we have the results for the OPLS model. And you can now see the rotation that I was referring to. OPLS has rotated all the predictively relevant information into the first component. We can see that for the violet colored batch, which is 55% salicylic acid, we seem to have a little split. One way to try to interpret that is to do a little highlight and use a tool that is called create plot xobs, and we can see that the reason for that split in the 55% batch is a baseline shift, and that is also something we have seen in just plotting the raw data, and that is something that causes that split and something we have to try to address very soon using spectral pre-processing. We can also, if we want to, just plot the loadings of the OPLS model. Usually you would make a scatter plot of the loading, but because we have spectral data, the line plot representation is more prevalent and also more meaningful. We don't need actually the Y loading, so I'm going to decouple the Q part and just visualize the P part. Instead of the variable number, we can actually use the spectral information, the wavelength information, and in addition we can also plot the first orthogonal loading of the model, and then we are producing the kind of loading plots that we were looking at during the PowerPoint presentation. Now, what we will do in the next stage is I will show you how you can try to remove the baseline differences by using spectral preprocessing, and that we can do under the Data tab, Spectral Filters. SIMCA has support for some 8 or 9 filters, and these can also be combined in different orders. We can combine filters in different orders, and that is called chaining of the filters, and you can chain up to 4 filters in a sequence. Here we are not going to use anything but standard normal variate, straightforward, so we select that one. Then we have a dialog where we can select if we want to do S&V on the entire spectral window, if we want to remove outliers or whatever, do on a subset. Here we're going to work with all the variables and all the spectra of the training set, and just finish like that. And then this procedure creates a new data set. So we actually have, if we look under the Home tab, one more data set now, which has the same name as the root imported data, but with an extension _S&V. And that means that we can very quickly compare original spectra with preprocessed spectra. And that is what we're doing right now. We can also remove that one. So in the left-hand part of the slide, or of the screen, sorry, we should now see the result of following S&V pretreatment. And in the right-hand part, we see the original spectra for the training set. And undeniably, the S&V has created a series of spectra that are much more aligned to each other. Another thing that will happen when you're doing preprocessing is that you usually decrease the complexity of the of the latent variable models, because you're removing systematic changes. So now when we go over and make an OPLS model for the S&V pretreated data, we would expect a slight reduction as far as the number of components in the model is concerned. We still have to center the data, because in the default skin of SIMCA, the default scaling is always unit variance scaling. So we are now working with the S&V preprocessed X matrix with the same Y variable, and we're calculating an OPLS model. And let's see if we get a reduction in the number of components. And we get that. We now have only 4 components of the orthogonal type. We had 6 components of the orthogonal type in the first PLS model. We can now compare the original OPLS model with the alternative OPLS model computed on the preprocessed spectra. So to the right, we had the initial OPLS model based on the original spectra, where we noted the split here. We had one group of samples here and another group of samples up here. And that split for the violet batch is now gone, as you can see. So it means that the preprocessing definitely has removed some of the baseline difference. We still seem to have a little systematic shift now for the batch that is colored using a yellow color, which would be the 51% batch. We can do a similar thing. We can plot spanning batches just to see, or spanning samples, to see where are the differences. And now there are some segregation in the upper or high numerical end of this wavelength window that is used. And part of this split here was one of the contributing facts leading forward to the researchers decreasing the spectral window in the stage 2 binary powder application, where they had fewer variables, which was a result of narrowing down the spectral window and also using a modified resolution. Apart from this, we have very similar statistics. So for the initial model and the model based on the preprocessed data, so the preliminary conclusion would be that the spectral preprocessing using S&V was a good thing to do. The last thing that I'm going to demonstrate is now to use this modified OPLS model for prediction. And in order to be able to make predictions, we have to import the prediction data. So I go to the Data tab, Import Dataset. I just have to save this. And then we're automatically guided over again to the import routine. And we now have to import the prediction data in the same way as we imported the training set data. And SIMCA will now try to match the different identifiers, and since the identifiers are the same, it will now automatically understand that the salicylic acid variable should be understood as a Y variable also for the prediction data. So we finish, and now we're going back into the main SIMCA. We'll kill a couple of things, and now we have also 2 more data sets. We have the data for the prediction set. The model that we will now use is the one that is highlighted in the project window, which is the active model, the last model, the OPLS model based on the SNV pre-processed data. When we are going to apply this model, we have to define what samples we want to predict, what samples do we wish to apply this model onto. So we go to the Predict tab. We're going to specify, first of all, we remove everything from the training set. We're picking up the prediction set data, and we want to use all samples like that. And the first step is now to compare the compatibility of the training set with the prediction set. How representative is the training set of the prediction set? And one important plot here is the so-called DMODX plot. Here we have the DMODX plot for the training set, and we're also making the DMODX plot for the prediction set. And now we want ideally the training set, which is on the right-hand side, and the test set, or prediction set, which is on the left-hand side, to have similar deviations from the model plane. And indeed, we have very similar distributions of the DMODXs, indicating that the training set is indeed representative of the test set. The next thing we can do is to look at the very popular plot of observed versus predicted. This is for the training set. We can also turn on the 1-1 line like that. And under the Predict tab, we can then also create a similar plot for the test set. So now when we have arranged the plots side by side, in the right-hand part, we have the results measured versus predicted for the training set. And in the left-hand part, we have the similar plot, measured data versus predicted data for the test set. And because of their similarity, the conclusion is that the model is very well founded, and it was this sort of result that inspired the researchers to move on also to the second stage. I think this is what I wanted to show you. This is a rather elaborate and voluminous webinar, but we had a lot of interesting things that we would like to present to you. Thank you very much for your time and attention, and I will very shortly be back to try to respond to any questions that you might have. So thank you so much for your time and attention.